have finished Unit 1. Now I want to start with Topic 2, Unit 1. And the heading then is matter. Now when I talk about matter, you must immediately know that all matter consists of particles. The particles have energy, so they can move. And what else there are? Spaces between the particles, and there are forces between the particles. What should you know at this point about the forces? Two things. Attractive and repulsive forces. We say the attractive forces in solids are very strong. In liquids weaker. In gases non-existent. And what about the repulsive forces? They only play a role when? Are there any repulsive forces in the desk at this point? No. When will the repulsive forces play a role? No. If I have a gas in a cylinder, are there repulsive forces? No. But if I try and compress the gas, the repulsive forces play a role. So we say when we compress matter, repulsive forces come into action. Okay. So in your textbooks then, the first thing that they say is matter is anything that has mass and occupies space. All right? Then they go and tell us the kinetic particle theory for matter. We've just had a look at it. Matter consists of particles. These particles have energy, therefore they can move. There are spaces between the particles, and there are forces, attractive and repulsive. And remember, repulsive forces only play a role when particles are forced together. You're all with me on that? All right, that's old work. Then the next thing that they go and have a look at, which is also nothing new, they go and have a look at states of matter and their interconversions. Another word for state of matter is the phase, whether it is a solid, all right, there's a solid, whether it is a liquid, or whether it is a solid, liquid, or gas. Now, they say a solid can absorb energy, all right, then it will become a liquid. We all know if water is lying on the floor a little while later we come back, is there still some water on the floor? Nope, it has evaporated. We say a liquid can become a gas. When a solid becomes a liquid, we call it melting. What do we call it when a liquid becomes a gas? A liquid becomes a gas? Yes, evaporation. All right, evaporation. We also sometimes find that some solids can directly form a gas. What do we call this? Sublimation. All right, now those three processes, melting, evaporation, and sublimation, all involve a gaining of energy. All right? If we go and look at the other phase changes, I'm going to do them in, okay, let's do them in red. When a gas becomes a liquid, what do we call that? Condensation, yes. We say the gas condenses. What happens when a liquid becomes a solid? Yes, it's either freezing or solidification. All right? So a liquid can freeze and it can become a solid. Then under very special circumstances, we sometimes get that a gas can directly go to a solid. What do we call this? Sublimation or deposition. All right, there's a new word. Up until this point, we've just referred to it as sublimation. All right, deposition from a gas to a solid. Now, all of these phase changes, freezing, condensing, and deposition, all involve a loss or gain of energy? Loss of energy. Okay. Now, I'm still busy with the phase changes. If I say to you, use the kinetic theory and explain melting, what words do you start with? Particles gain energy. What do they do with this energy? They move more and further apart. Do they completely overcome the attractive forces? No, they partially overcome the attractive forces, and it forms a liquid. If I asked you, use the kinetic theory and explain evaporation, we say particles gain energy. What do they do with the energy? They move more and over greater distances. Okay, in other words, we say they partially overcome the attractive forces, forming a liquid. That is, if we have a solid. If we have a gas, okay, if I have a gas, if I have a liquid, sorry, if I have a liquid, then we also say particles gain energy. What do they do with the energy? They move more and over greater distances. Do they partially overcome? They completely overcome the attractive forces and they form a gas. Do you understand? All right? If we go and have a look at these phase changes, okay, going from a gas to a liquid to a solid, how would we word it? We will say a gas, particles will lose energy, therefore they move less, okay, less, and the attractive forces can pull them together, forming a liquid. All right. Now, if I say, let's just draw a line there. If I say I don't have a gas, but a liquid, particles, if they lose energy, they will move less. The attractive forces will pull them closer together, forming a solid. That one gains energy, that one loses energy. If it gains energy, what does it do? It either partially or completely overcomes the attractive forces. Remember, in a liquid, there are still some attractive forces. Then we will say particles gain energy. They completely overcome the attractive forces and it becomes a gas. Yes. Gases have completely overcome the attractive forces. Liquids have partially overcome the attractive forces. All right. That is very important. Okay. Now, the next thing then that we look at is there on page, where are we now? Page 78, 79, diffusion. What is the definition for diffusion? Yes, very good. It's simply the spontaneous movement of particles. So, what is diffusion? It is the spontaneous movement of particles. And usually it's a liquid or a gas. Okay, now, there are many definitions, and you tend to confuse diffusion with osmosis. Remember, osmosis is the movement of water particles. Diffusion refers to the movement of any gas. Now, in some books they will say, diffusion occurs from a point where there is lots of the stuff till everything has spread out evenly. Yes. But what does that imply? Is there any diffusion in the air around us now? Yes. If nobody is in the class and I close up all the windows and I keep the temperature constant, is there any diffusion in the class? Diffusion never stops. It's a spontaneous movement of particles. The definition that they use and say that diffusion occurs when particles move from a point of high concentration to a point of low concentration implies that somewhere along the line diffusion stops. Does it ever stop? No. It never stops. So if there is no concentration gradient, does diffusion stop? No. If there's no concentration gradient, diffusion continues because particles have energy. And if they have energy, they can move. We spoke about the absolute zero and Kelvin temperature. When is the only time that particles will have no energy? When they are at 0 Kelvin, at the absolute zero. Anything above that, particles have energy. The moment they have energy, they can move. Okay. So just be careful when you word the definition. I like the one, spontaneous movement of particles. You can go and add in from a point of high concentration to a point of low concentration. But please keep in mind, if there is no concentration gradient, diffusion still continues. Now over here, I have a picture of 2 gas cylinders. In the bottom of the one gas cylinder, I've got some nitric acid and some pieces of copper, and it makes nitrogen dioxide gas. All right. So the gas is produced down here at the bottom, so there's lots of gas there. We have a piece of filter paper between the 2 cylinders. And if we leave this to stand still for about 10-15 minutes, we find that the gas will fill this bottom jar. And the next thing you will notice that it is spreading to the top jar. How can the gas get through the filter paper? The kinetic theory tells us there are spaces between particles. The filter paper is made up out of a material that has got a specific size space, and the gas in the cylinder is small enough to fit through the spaces. So will the filter paper prevent diffusion? No. It might slow it down a little bit because some particles will bump and then they don't hit an opening, but other particles will bump and it hits the opening and it will go through. Do you understand? But once it's in the next container, it is going to spread through the container. And if I left it to stand overnight, eventually everything will spread equally. At that point, would diffusion stop? No, it goes on because there is always some energy. Okay. So, the next thing then, they say over here, why does the gas move through the filter paper? The filter paper has got spaces between the particles, and the gas molecules fit into those spaces. Do you follow? Okay. All right then. Factors that affect the rate of diffusion. Now the rate of diffusion tells me how fast people, there are 3 things that affect the rate of diffusion. In other words, how fast or how slow. The first factor is temperature. And that is just very simply, temperature is a measure of the average kinetic energy of particles. So if something has a higher temperature and something has a lower temperature, the one with a higher temperature will have more energy. If it has more energy, it can move faster. Okay, so temperature, the hotter, the faster. The opposite also holds true. The colder, the slower. Okay, if I took this experiment over here and I put it in a fridge, it's going to take much longer to diffuse through and fill the top container. The second factor that influences the rate of diffusion is the phase of the substance. Liquids tend to diffuse slower than solids, gases. Why? The attractive forces in liquids are non-existent, and in liquids are weaker than in solids, but stronger than in gases. So there are still attractive forces holding the liquid particles together. But in gases, are there any attractive forces? No. So they are free to move. There's nothing holding them. So gases tend to diffuse faster than liquids, and liquids diffuse much faster than solids. Now your syllabus sort of ignores diffusion in solids. There is some proof that diffusion occurs in solids, but it takes very, 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 very long. If I could take a block of gold and I could put it against a block of lead, after a couple of years, maybe 100 years, I could take a sample from the edge of the gold and I'll find a little bit of lead in it, and vice versa. In the lead I'll find a little bit of gold. But it's very, extremely slow. It's so slow, we just ignore it. Okay, so we don't bother with diffusion in solids. Okay, here's a very well-known experiment. Diffusion of hydrochloric acid and ammonia. Hydrochloric acid is this one. There's hydrochloric acid, and you would put it on a cotton wool into a glass tube, and the other one is ammonia. There we have ammonia. I put some of that onto a cotton wool into a glass tube. If I stood in the laboratory with my bottle of ammonia and hydrochloric acid open, I will find, if I hold the bottles close together, that a white smoky substance is formed. What happens is hydrochloric acid reacts with ammonia, forming in a 4Cl, ammonium chloride. There we have ammonium chloride. Okay. And ammonium chloride is this white, smoky fume that you get. Now, if they go and do this experiment, they have to make the experiment fair. So in the first place, this glass tube must be perfectly horizontal. If it was hanging at an angle, gravity would help pull the one gas down. Okay? So by making it horizontal, the effect of gravity pulling it down does not play a role because it's not moving vertically, it's moving horizontally. Okay? That's the first thing. The second thing is, you've got to get the ammonia and the hydrochloric acids on the cotton wool, and then you have to push it into this tube simultaneously. Why? Why can't I first put in the one and then take my time and put in the other one? Yes, because the moment if I put that one in first, the gas is going to start diffusing. And then this one is not yet there. So there's nothing to diffuse. That test wouldn't be fair. So the samples must go into the tube simultaneously. All right? Once we've done that, you can now sit and look at what will happen. And then after about sometimes 10-15 minutes, we find that it forms a smoky white ring. But where would we expect to find that ring? We would have expected to find it in the middle, but we don't. Why don't we find it in the middle? The one gas diffuses faster than the other. Okay, now, would it be temperature that makes the one diffuse faster than the other in this experiment? No, they are at room temperature. Both have the same temperature. The next factor that affects diffusion is the size of the particle. Bigger, heavier particles diffuse slower than smaller, lighter particles. So what's the conclusion from this experiment that we've got over here? Can you see that ammonia moved faster than hydrogen chloride? So which one is lighter and a smaller molecule? Ammonia is a smaller and lighter molecule, and we will see this when we do a little bit of the masses of the atoms, the different atoms and the compounds, okay, when we do a bit of stoichiometry. which is a little bit later on. Okay, now the question, explain why the white fumes of ammonium chloride is formed closer to the hydrogen chloride and not in the middle of the tube. The ammonia gas moves faster than the hydrochloric acid gas. All right. Then we get something called Brownian movement, and all of you have seen Brownian movement. We get Brownian movement, for example, if you sit inside a room and there is sun shining onto the window and the curtains are closed, but there's a shaft of light falling through. The little dust particles that bounce about in the air, that is Brownian movement. The definition of Brownian movement is an erratic movement of solid particles suspended in a liquid or gas. The dust particle is a solid particle, the air is the gas. A very well-known experiment that was done was with pollen grains in water. The pollen grains are very tiny, solid particles. The water is the liquid. And you can see this erratic movement. Going back to diffusion, we said it's a spontaneous movement of particles. I skipped this part. And then I just have two pictures. In this one, I put solid particles known as potassium permanganates. It's the purple crystals, very soluble in water. And you can very clearly see from where the soluble particle is, as the particles start dissolving in the water due to the movement of the water, we find that we can see the solid particles rising. A tea bag in water, you can see something is dissolving in the water and it starts moving. All right, before you even stir it.
Football on GoTV, so he traded being a best man for being a best fan. Miriam stood her date up just for this matchup. Albert and his family had plans, but they couldn't miss this, and neither can you. Because this new football season, this is football worth watching. Get a GoTV decoder and 1 month of GoTV Max for only $349 to get all the football action. GoTV, live it, love it.
With Unit 2, and Unit 2 is about the structure of the atom. Now in grade 8 and grade 9 you've already done atomic structure. We know an atom consists of what? Protons, neutrons, and electrons. At this point you should know protons and neutrons form the nucleus, and we find the electrons around the nucleus. Alright. Now, in your grade 10 work, they want you to know a little bit about the history of the development of the atom. How did it come about that we ended up with a model that we accept today? Now, in the early years, I mean, this is 400 years before Christ, okay, Democritus, they said matter consists of particles, but they did not realize, or they did not know, they said these particles are not divisible. So there's the first part of our kinetic theory. Matter consists of particles. Can you see where they fetched the theory from? Okay. Then, in the early 1800s, John Dalton, he came up with the idea, or they tested it, experimented a little bit with matter, and he said, matter is made up out of particles, but he called these particles atoms. Okay? He said, I cannot make an atom, and I cannot destroy an atom. So if I need to make iron legs for my table, I need to mine iron. I can't click my fingers and there I've got some iron. I can't make it. I can extract it from the iron in the ground. All right. But I cannot create atoms. The earth, everything that's on it, all the atoms is all there is. Okay, that's one of the problems with plastic bags. Plastic bags hold carbon in the plastic. And it doesn't want to degrade, it takes very long. So carbon is taken out of the carbon cycle, because there's a cycle of decomposition where the carbon gets put back into the system. Eventually plants photosynthesize, take up the carbon dioxide and make food with it. All right. So he said atoms cannot be made or destroyed. They said also atoms of the same element are identical, they are the same. That's fairly logical, isn't it? Okay, gold atoms will look like gold atoms, and oxygen atoms don't look like gold atoms. All right. They say atoms of different elements are different. Well, if atoms of the same element are the same, atoms of different elements are different. All right. It's just, I think, to reinforce the idea that each atom of a substance is unique. All right. Then they say atoms can join together to form larger particles. Okay, there we start getting onto the concept of, oh goodness me, I've got certain elements and they can go and stick onto each other and make something. All right. After Dalton, about 90 years later, now you must know how long they fiddled with this to reach a point where J.J. Thomson said the following. He said, matter is not only made up out of particles, but he said, this particle has got something in it which is different from the original particle. And the image that you can have is like if you have a raisin bun. You've got the bread dough, and you've got raisins distributed inside it. Now, Thomson said the bread dough part is positive, and the raisins stuck in it is negative. So the concept of charged particles is now starting to form. All right? I'm sure that they accepted the billiard ball theory, and then they would maybe start investigating effects of static electricity. And now the billiard ball theory can't explain that. So now the next step is to go and fix or change the model or the theory to fit what you want to explain. So Thomson said, well, we have a solid mass that is positive, and distributed within that solid mass we have negative particles. All right? He came to the conclusion that there are negative particles. He suggested the negative particles were distributed within the positive mass. Would the negative electrons be free to move? No. Okay, so there's the shortcoming on his theory. So a couple of years later, you will see that was 1897, then about 14, 15 years later, we got Rutherford. And Rutherford said, but this theory of Thomson does not explain static electricity. We've now got the concept of charges, opposite charges that should attract and like charges that should repel. And he went and he changed the model and he said, atoms have a dense positive center. Okay, just a solid positive mass. And around this solid positive, we have got on the outside of it electrons. So he said the nucleus consists of a proton. And around this proton nucleus, we get electrons. Now it's easy to understand why the electrons stay around on the outside, because positive and negative attract. But what's the problem with a positive nucleus? Does it only have one positive charge? No, it depends on the number of protons. And what will one positive and another positive do? Repel. So will a nucleus stay together if it's made up out of different positive particles? Nope. Okay, and this led them to realize, but this model of Rutherford is not yet totally there, there's still something wrong with it. And then we find 2 years later, in 1930, Niels Bohr, now this term Bohr structures. Okay, what did Bohr tell us? He said that the electrons move around the nucleus in specific shells or energy levels. Okay? The size and the shape of the shell will depend on the amount of energy of the electron. Now, we don't really go into the size and the shape of the shell. We just picture it as if there's the nucleus, we have a shell around it, and another one, and another one. Okay, don't worry too much about the shape at this point. Now, he also said then that each shell can hold a specific number of electrons, and what's the pattern we use when we draw Bohr structures? The first shell has got 2 electrons. The second shell can take up to 8. The third shell, 8, etc. All right. Now, Niels Bohr was fairly close to the truth. But we are still stuck with this problem of the nucleus. If it's one solid positive particle, yes, it'll stay there. But the moment it consists of more than one positive particle, it's going to repel and we'll have an unstable nucleus and it's going to fall apart. So the next scientist was Chadwick, and you will see it's approximately 20 years later. Chadwick came to the conclusion and he said, we're missing something. We now have protons that are positive and electrons that are negative. But what can make the protons stick together? A neutral particle. All right. And he said, we have a third particle, and he named it a neutron. And he came to the conclusion that neutrons have no charge. All right. It's found in the nucleus, and it has the same mass as a proton. Okay. And that brings us to the structure of the atom as we know it today. We have a nucleus consisting of protons and neutrons. Protons, we say, have a positive charge of 1. Neutrons don't have a charge. All right. Around the nucleus, we find electrons in shells. If my atom is neutral, the number of protons will equal the number of electrons. You follow? Okay? So that is the structure of the atom as we work with it now. Now, the model of the atom, it's just, it's a theory. They can't concretely prove it. But because this theory explains what we work with satisfactorily, we accept it. But at this point, this theory has been developed further. Okay, there are particles known as neutrinos and quarks. All right, but we don't work with it because for the level at which we work, this model that we have over here is good enough. It explains what we need to explain. So this then is the structure of the atom that we are going to work with. Now, the next step is to go and have a look at the elements or at the periodic table. Now, what is the periodic table? It's a classifying system where elements are arranged according to the number of protons they have. For example, hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, boron is 5, etc. The number of protons determine which element you have. Elements with similar properties are placed together. For example, the group 1 metals. They have similar properties. Can you remember from last year, low densities, soft, low melting points, fairly reactive, etc. Okay. I'm going to hand out a periodic table, and we are going to have a look at these things on the periodic table. Now, the periodic table that I'm handing out is the exact copy of the one that is in your syllabus, and it is this one that you will get in the exams. Okay, so if you have the exact one that you get in the exams, you can start getting used to it, and you will know how to work with it. Okay. Now, in your textbooks, there is also a periodic table. Now, I don't want you to go scratching all over the textbook. Please fill in the notes on the periodic table that I've given you now. Okay. What is the first thing that we can do on this periodic table? Draw the step. What does the step do? Separates metals from non-metals. Okay, so where will the step go? Remember, hydrogen is a non-metal. Okay, so the step goes there, between hydrogen and lithium. Now, lithium and beryllium are metals, so it goes down one little block there. Okay, boron is a non-metal. Aluminium is a metal. Silicon is a non-metal. Germanium is a metal. But astatine, arsenic is a non-metal. Then between antimony, tellurium, polonium, astatine, and there we go. There we have, you see, yeah, you can just ignore it. I think your periodic table ends there. All right? The step separating, what do we have below the step? And what do we have above the step? So do you have to go and learn all the elements out of your head, which are metals and which are non-metals? No, you go and look on your periodic table, because in every exam you will get this periodic table. So if I say to you, name 10 metals, you take your periodic table and you take any of those 10 metals. All right. Which one is more, metals or non-metals? There are more metals than non-metals. Okay. That's the first thing that we have to do. Now, the next thing, okay, we've done metals and non-metals. Now, the next thing is to go and identify which elements are solids, which are liquids, and which are gases at room temperature. Now, let's go and start with the gases. Now, there are only a few gases, and I'm going to use blue to identify the gases. So, hydrogen is a gas. Nitrogen is a gas. Oxygen is a gas. Fluorine is a gas. And chlorine is a gas. Then, all of these elements there, all of them are gases. We call them, this group 8, are so-called noble gases. Can you remember why they're called noble gases? Yes, they don't want to form chemical bonds with other elements. Why don't they want to react? Can you remember that? Yes, the elements have filled outer shells. And if an atom has a filled outer shell, it's in its most stable state. It doesn't want to do anything else. All right. So now we have got our liquids. So liquids are in that color. Gases. The next one are the liquids. Now that one's actually easy. How many liquids are there? 2. Can you remember which they are? Mercury and bromine. The one is a metal and the other is a non-metal. So where's mercury? It lies over there. Can you see I've got it in a green block? Like that. That's mercury, is a liquid, and the other one is bromine. There it is. 2 liquids. One is a metal. How do I know mercury is a metal? It lies below the step. How do I know bromine's a non-metal? It lies above the step. Alright. So, now we have got solid, liquid, gas. And the next thing we must have a look at is diatomic elements. Okay, now, which elements are so-called diatomic elements? Okay? Now, which elements are diatomic? We have to mark them. Now, I am going to use, now we've got blue and we've used yellow and we've used red. Okay, I'm going to mark them in black. Okay, so I'm going to mark the diatomic ones with my black marker. So, hydrogen is diatomic. Nitrogen is diatomic. Oxygen is diatomic. Fluorine, chlorine, bromine, iodine, astatine. We won't work with the bottom ones at all. Okay? So, the diatomic ones. What does it mean if it's diatomic? Two atoms of that element are bonded onto each other. In other words, if I could scoop up a bucket of hydrogen, I will find I don't have separate atoms. I have two atoms and they are stuck onto each other. Alright, if I could draw a picture, hydrogen would look like that, the two atoms sticking onto each other. Okay, it means two atoms of the same kind. Can you remember what type of bond we find? Yes, covalently bonded. So, diatomic elements are two atoms of the same kind, covalently bonded. Okay, so how will I write the symbol for hydrogen? H2. Oxygen, O2. Nitrogen, N2. Chlorine, Cl2. Bromine, Br2. Iodine, yeah? Yes, and fluorine. Okay. The diatomic elements. When a diatomic element wants to form a compound with something, let's say, for example, these two want to react. Okay? I will have hydrogen and I will have oxygen, but what is going to be formed is water. So what must first happen is, if that is my hydrogen molecule and that's my oxygen molecule, they must break apart before they will form the compound. Okay. So, yeah, you have to break them. They have to be in the form of separate. I don't write the two because here the formula for water, the stuff that is formed as a new formula. Okay, but where you wrote them separately, there and there, you write them as they are diatomic. Okay. Remember, we balance the equation eventually. There we go. What's the next thing we must fill in? We have now got diatomic. Okay, now, some of the parts of the periodic table, we know that it's divided up into vertical groups. Do you agree with me? Yes? How many groups do we identify? 8. We ignore that for the time being. Okay? Just ignore it for a moment. We have got 1, 2, 3, 4, 5, 6, 7, 8 groups of elements. Now, elements are ordered together in groups because they have similar properties. We've just spoken about the noble gases. Now, I quickly want to clean off this board a little bit. I need to write some stuff in on it again. All right, we said the vertical columns are the groups, and we differentiate group 1, group 2, group 3, 4, 5, 6, 7, and 8. You'll see your periodic table has a Roman numeral at the top of the column. We'll get to that in a moment. Okay. All right. Now, the groups have got special names. Group 1 elements are known as alkali metals. The group 1 metals, this group here, okay, we sort of ignore hydrogen, are known as the alkali metals. The group 2 elements are known as the alkaline earth metals. All right. What other names do we know? What do I call them? Yes. Group 8 is known as the noble gases. What is group 7 known as? The halogens. All right? So now we know alkali metals, alkali earth metals, we've got halogens and we've got noble gases. What is left? What Wayne asked. Transition metals. What forms the transition metals? This block here, that is not divided up into groups, okay? These elements, they are the so-called transition metals. Okay, talk about lanthanides and actinides, we don't bother with them. All right. So, now we know what the different parts of the periodic table is called. Okay, we know which elements are solids, we know which elements are liquids, we know which elements are gases. At this point, we know which ones are diatomic. All right? And as we start off with bonding, etc., we will go and have a look at exactly what and how we will work with this periodic table.
Namibia is known for its beautiful wide open landscapes. However, these deserted spaces also pose numerous educational challenges in our country's rural areas. Because of this, many learners are denied access to proper teaching and learning. At EduVision, we believe that education is the starting point to a journey of endless possibilities.
Very soon, we are going to see e-learning. Soon and very soon, we are going.
The plan for EduVision was to identify areas in Namibia that do not have the proper learning resources, a working school or an education center.
Hallelujah, hallelujah, we are going to see e-learning. No more dieting. No more dieting.
My name is Philip Smith. I'm the principal of Educate Academy in Otjiwarongo. The project EduVision, the e-learning program, started in 2017. With a project like this, obviously telecommunication, internet connection is a major thing that needs to be sorted out, a logistical challenge. And the fact that we chose Chunkwe Secondary School as the first school didn't make it easier for ourselves. It's very far from Otjiwarongo, it's far from Windhoek. So the internet connection was a big challenge first of all. So with the help of the telecommunications expert Paratus, they made this dream come true with internet connections via Windhoek, Otjiwarongo to Chunkwe and then back, the whole process. like I said, it's interactive whiteboard, so the internet speed, capacity of the connectivity and so forth plays a major role. And so Paratus made this dream come true, and they were on board from the first moment. And so we're grateful for Paratus.
The project offers teaching assistance of a high standard in science to rural secondary schools within the learner's own community by means of e-learning. This entails the following: live transmissions of lessons from an equipped teacher in a different location to the students in rural areas, students using their own cell phone, tablet or computer to recall each lesson, and interactive lessons, as well as the use of a smartboard as a teaching aid.
So if you look ahead at the next 3 years, we get information from the Ministry of Education. The future is very bright. So I think there's a lot of schools who can benefit from this program. Like I mentioned before, finances obviously plays a major role in a project like this. So we're very thankful for all the sponsors that are on board and still on board after almost 3 years of the project. So as long as people from the private sector can get involved, I think we can reach many schools in Namibia, because this project made a good start now. We're already seeing some positive results, and we can just call on all the private sector corporate sponsors to come on board and join in this very, very positive project.
It is EduVision's goal to prepare and guide learners in order to make the modern world they are living in accessible to all.
My name is Magdalena Neoma. I'm 18 years old and I'm doing my first year at UNAM Komando campus, and I completed my grade 12 at Tsonkwe Senior Secondary School. I'm doing education, so I'm gonna teach at Tsonkwe Secondary School, because there I really need to go there and motivate the learners. EduVision helped me a lot. It assisted us in teaching for mathematics, physical science, and biology. And it also, we get to exchange learning from other schools like Educate, whereby they teach us, and that's the most thing that we benefited from. Studying without EduVision was so challenging. And when EduVision was introduced at our school, things become more easier. The time where EduVision was not introduced, we were so slow in learning. And when EduVision came, introduced at our school, my learning speed increases. Things were kind of boring. And when EduVision came, my mind changed the way I think. I'm really grateful for what EduVision gave us. Our class of 2019 was the first group to make it, to perform very well at Tsonkwe Senior Secondary School. So it should keep up the spirit. We need that. It should continue to support us.
EduVision aspires to ensure that equal opportunity is offered to every learner in rural areas to tap into his or her own potential while working in an environment which views disadvantages not as obstacles but as unique attributes that can be regarded as powerful assets when given the proper opportunity. At EduVision, we believe that dreams are the foundation of knowledge and hope always triumphs over experience.
No more problems. Everything is proper. EduVision.
Say, me I dey pray single day for the kingdom. Oh Lord Father God gave me talent and wisdom. So I dey sing for the people, the streets they need peace and eternity power like Simpson. In this music I'm doing, I'm telling a story. My dear people, I better keep listening, cause I'm busy doing the most. I'm busy doing the most. Oh yeah.
Peace, ain't gonna touch my soul. I ain't doing them. These lyrics ain't gonna shift my mind. I sing them. These rhythm ain't gonna move my heart. I dance it, cause I'm in the seat of my dress, my soul. I sing them. Go, ani gongo bongo. Ani landi go solo. Dongo, loya solo. Keje vikungondabo. Kwenye veli metata Kenya ba kanga ulimo makumba patopa mada shana kulio shana kulonga no maha etaishi tashili washe otwa adigajalo Versace I'ma pull up in a Bugatti wanna live the dream life that I see on TV go ani gongo bongo ani landi go solo ndombolo ya solo.
Me I dey pray single day for the kingdom. Oh Lord Father God gave me talent and wisdom. So I dey sing for the people, the streets they need peace and eternity power like Simpson. In this music I'm doing, I'm telling a story. My dear people, I better keep listening, cause I'm busy doing the most. I'm busy doing the most. Oh yeah.
Peace ain't gonna touch my soul. I ain't doing them. These lyrics ain't gonna shift my mind. I sing them. These rhythm ain't gonna move my heart. I dance it, cause I'm in the city, I'ma chase my goal.
Allow me to reintroduce myself. My name is Juice Boy. When I say I don't play fire, I don't mean toys, cause it is what it is and it's coming what it was they back then. Hanasikia mulombo luano Osike muate ngalango ngwano Twali kuimba ngano nganya Osikina muhala nando kuja kwano. I do this music for life, you they live life for life. We be all cool for life, cause at the end of the day it will end in this life. I am here to teach you life.
Go, ani gongo bongo ani landi go solo Ndombolo ya solo Keje vikungondabo. If these beats ain't gonna touch my soul, I ain't doing them. If these lyrics ain't gonna shift my mind, I sing them. These